All right. So, okay, actually, so we're doing a review, but a couple of days ago, running across this little picture that is very related to, closely related to what we're doing here. So let me just show you what it is. So anybody knows what LLM stands for?
Light language model?
Yes. So just one picture, and it explains what. Okay. What the link is. So LLM, and so what is the point? Okay, so the data is about language. Okay, it's how the computer is supposed to understand words based on data. Okay, so and then how the answer is create the space with words as points. Naturally, it's not two-dimensional, but multi-dimensional space, maybe 1 million dimensional space, doesn't matter. And then, but the point then, and then what do you do? How do you measure distances in such a space? And the answer is, as you can see, that formula on the right, there are actually two things to consider. One, well, you can see the point. Why do we want to measure distances? So that, for example, cat is close to the dog, cat is close to dog, but far from banana. Okay, so it has to be good enough to separate, say, the fruits from animals, but on the other hand, you don't want to say that cat is the same as dog. Okay, so it's a big problem. But mathematically speaking, what is that we do? We're measuring distances to begin with in this multidimensional space, and the answer is how we do it is basically this: the term in the denominator, Euclidean formula. Once again, everything will be reviewed, and at some point we'll be just about the same place. But it's online, and a person tried to fit everything in one picture, so that's interesting to see. And so one way just to measure distances using the Euclidean formula, which is basically the denominator in that formula. And the second one is actually to the angle between them, rather than considering the distance between the 2 points. Consider instead the angle between them, like this. Okay, so so the direction matters, and then there's this cosine formula, which comes from trigonometry. That once again you can figure out if you know the coordinates of points, you can figure out the angle between them, vectors literally, by this formula, which is, as you can see, right. Okay. So that this is geometry. I already remember I started with example of to explain what linear algebra was about. Started with example of mixtures, and once again, behind it, the two coffee is just like you have two types of coffee there. In that problem here, you have four words that to talk about. They're only two dimensions. So of course, it's never lower dimensional, but the only way to do it, if you want to make a picture, you just pretend that the dimension is very low. But so the difference is the algebra, you only need algebra to do the mixture problem. And here we are doing this geometry. Okay, so measuring, doing algebras, addition, subtraction, whatever, that's algebra, and measuring distances or angles, that is geometry, analytic geometry. So we're not literally measuring anything. We are computing it because that's the space of words is made up. And so we have to make up how the geometry of it as well. And so that's the easy geometry is this. It is Euclidean geometry. So it's hard to believe that that geometry that we choose for words is the same as the space we choose or acquire for the physical space. But that's actually the it comes so naturally, so almost every time it happens, because that's first thing that comes to mind is how do we measure distances? Well, the same way as we measure in the physical space. So anyway, so like I said, that this is just a little picture. Any questions about this? Okay, so all right, so we are doing a review, and just a review what we are reviewing concepts that you have seen many times a long time ago, probably, such as sets, functions, relations, functions, and then we'll just review them on such an abstract and basic level, so that from scratch. Okay, so including graphs, for example, here as you can see, there is this is my function. This is you can with arrows related, rather. You can also have like a flow chart computing once again that relation, yes or no. Okay, yes or no. You can put that yes or no as a cross. If it's yes, put a cross in the table, and then you can actually flip that table. That's the original table on the left. You have 5 crosses, depending on which game is played by the boy. And then on the right, it's the same. These are the same axes, just flipped. Okay, and so it's the same data. Makes no difference what comes first or second. And that's a visualization, and that brings us to the example that I brought up at the end. Is the our table is just rotated will produce a graph. What we literally call in when we speak of functions, we in calculus, pre-calculus environment, that's what it is. The inputs are horizontal, outputs are vertical, and we plot these points, except of crosses. We usually would put dots over there, but that's the only difference. Okay, and so that's literally what we're doing. Except now, once again, as I promised, we now review functions, which is exactly the same thing. But once again, we have to be very, very careful about the definition. What is a function which is not a formula? Okay, so you've seen many formulas before. That's the formula will produce a function if it is unambiguous. For example, you cannot have plus or minus. Okay, so but to understand it in a more general environment, more abstract environment, it takes a bit of preparation. And the why, once again, the point why we go so far into let's face it, pre-calculus is because the entities that we're dealing with are not necessarily numbers anymore. So even if there is a formula, is there a formula or not? It's not necessarily formula function. So because we'll have functions, we have points, we have vectors, we'll have functions of functions. Okay, so then let's go abstract here, and then that's the transition that we make from relations to functions is to make something, make a special function, a special kind of relation. Relation any bunch of pairs of inputs or of x and y's. Okay, and here we are the difference between the two is in this question. What sports has the boy played today? Maybe multiple. Okay, and which can be turned around, right? So it can be turned around and asked. The question may be asked about in the kind of passive voice. The question could be what boys played this game. Okay, so it really doesn't matter passive or not. The answer is the same. So it will produce a pair of boys are paired up with balls. But this one is new in the sense the question is quite a bit different because it always has only one and only one answer. Okay, so that's the difference between relation and function is everybody's forced to answer the question. So that who is Ned actually did not choose, but if prefer to play, you'll have to choose one of the games as your answer. And secondly, you cannot choose two. So that's what makes up a function that two requirements to be satisfied. One and only one answer. Okay, so once again, picture on the left, arrows drawn any way you want. On the left, every boy has got to have an arrow and exactly one arrow, no more nor less. That's what it makes up a function. So once again, these are how we visualize it. You can write a sentence for each of them. You can plot an arrow for it. The once again x arrow y. That's our, just like with relations, we put a label on top of it. That's the name of the relation. And then once again, this is the rule that's to be tested. It has nothing to do with numbers or any point entities that we might be dealing with. It's the same story. So naturally in the computing context, which you certainly will see. So function then is a kind of computing device. And what's special without it is that you plug in, you should be able to plug in anything that from a certain set. You can plug in anything in it, and there always will get an answer, but no more than one, meaning that no matter the day of the week, it produces the same answer. So that's what the function is. Some kind of procedure that turns inputs into outputs, which is where actually right, the words start to make sense, these words, because if it is a relation, there is no input and output. Which one first, which one second doesn't matter, but here it does. Okay, so the requirement applies to x's, not to y's. So I'm not saying there is exactly one x for each y, and you can see it's not the case. A baseball has nothing, and basketball has two. So that standard does not apply. Is not applied to y's, to the outputs. Outputs, there is no restriction on them. So once again, that's notation. Literally, that's the way it's written in text. So x, arrow y, and then you put f in front of it, or you put f as a label. Okay, so it allows you to build diagrams, that kind of notation, especially the second one, because you can continue on, and then maybe you have z, and you call it g, and then you can envision with this notation a long multi-step procedure, multi-step procedure, each of which is a function. Okay, so that's what you would be doing in computing, right? But the notation, the mathematical notation is very fitting here. Okay, so once again, if we go back to the table, okay, so what's so special? Our condition is that there should be input one, exactly one output for each input. Which means that there's exactly one mark in each row. Okay, so go horizontally and you see one mark. Naturally, this is the algebraic notation. So once again, you've seen this before with numbers, but just as well, the nature of the inputs outputs is not restriction. Okay, we can put anything as the input, and once again, I put in parentheses. That's the standard standard notation, algebraic notation. If you prefer, you can do arrows, you can do process markings in the table, or this is the if you were to write formulas, that it is the formula, even though it's there is nothing to compute. It already has been computed, and so inputs in parentheses. And so it's one of the 5 boys, and on the output you put one of the balls to indicate the answer once again. It is entirely abstract. So you're dealing with data. Pretty much, this is what it is. A function of data. Both input is data, not a number, and output is data, not a number. Okay, so that's how we write it. As I said, x input is inside the parentheses, output y on the outside. You can put an arrow here also to connect them together. Either way, it is notation is pretty good. You know, sometimes notation are very uncomfortable, and it is if anything, then this is a bit of a complaint usual, because you have to read it from right to left. F of x, we read it from left to right, but really in the the order of things, or x, f, then y, right? F, x, you know the input, then f applies, right? So x, f applies, and then y is the output. So that's the order of things, and when the algebra is read then from right to left. X, f, the algebraic notation. Okay, so once again, you can once you have this, you can write in words, because the names are unambiguous for either boys or for the ball, for the games, and then so you can just write input output. Once again, with processing data, the notation of that you learn about numbers still applies entirely to abstract or unspecified entities, and you can do algebra with them. So renaming things is a good idea. You can rewrite our five statements over here equal about our function, only 5 possible outputs, and you can either present them with crosses, excuse me, crosses on the left or on the right. Doesn't matter which one. You can do the graph. You using a table on the left, I'd say. And definitely the right one is what we are the most used to, and that the input is horizontal and the y output is vertical. But it's the same data. Okay, so it's just tradition to put x's and y's in this relation to each other like this. Okay, that goes back to Descartes himself, the Cartesian system. Okay, so because I renamed them from every boy has a name, but also you can assign a number to them. So that's literally what you see on the right is the Cartesian system, where numbers correspond to each other. Of course, there is no particular way or any meaningful way to number either boys or the balls, and so that is certainly artificial. But it just the purpose is to link what we're doing right now to something that you've done a while before, Cartesian systems and graphs of functions as a bunch of points on the Cartesian plane. Okay. Yeah, that's what the graph is. And once again, you can see those arrows. Those arrows are still there, arrows from X to Y. X's are horizontal. How do I link them with these purple arrows from, once again, X 1 to 1, 2 to 2, 3 to 1, 4 to 4, and 5 to 4. Okay, so that's how you can get from one axis to the other. And then what you do is where you turn, where you have to turn, that's where you put a dot. So, and then if you take these 5 dots together, what it will give you is the graph. Okay, so that's the graph made of only 5 points, but nonetheless, it works out exactly as with numbers. Okay, so spreadsheet does it automatically. If you have 2 tables, we've already seen it. Once again, they could be data, it could be numbers, better be numbers, and then literally you just highlight, insert chart, and then you have that graph on the right. Okay. So this is the data you might encounter this in the academic environment. So I have on the left, I have a list of faculty. On top, I have a list of committees. Okay, so and with crosses is the person is in the committee. C is the on the committee and also the chair. So even though the data arranged this naturally in this way, this is a very naturally a way to put it. Where do you see functions? Do you see functions in this data? Well, first of all, you do see a relation, right? So you have x's on the left, say the faculty, and the committees at top, and the crosses, including c's, are a relation. That's it. So that always works out. But what about functions? Do you see functions?
Say no. Say there's no function, or at least readily apparent function. That's like you plug in something and you obviously get a Y.
Well, I'd say the inputs, the name of the output would be.
I mean, would it be considered ambiguous? It
Well,
is like
what you're saying is that if we look at the crosses, for example, we're getting our relation, but not a function. Because why not?
Input has multiple outputs.
Right, exactly. So that's why it's not a function. What if I concentrate on c's? Is the function? So forget about x, is only c's. What's wrong with that? Is it the function? Not every input has output, so it's not a function either. Okay, so neither crosses, nor c's, nor crosses with c's combined together produce a function. I still say there is a function here. You have to just take a different look. There's a function there. What if we go backwards? Well, okay, okay. Well, what you're saying is let's throw people out who are not on any committee. Okay, and then we can make what? And then okay, so suppose we do where's the function? You still have multiple answers, multiple outputs for the same input. Backwards, I mean, what if the inputs are the committees, not the faculty? You see? Every committee has exactly one chair. That's a function for you. So that the function then works this way. Okay. So committee chair within the faculty. Okay. So yeah, so that's how the data works. So when you have two sets, you can have relations, and it's the same relation. I could flip the table, it will remain the same relation, but if it is a function, then I have to be careful and specify which one is the inputs, which one I want the outputs. Okay, so here's another one. Soccer, so I don't remember what was the Liverpool or something, whatever is the soccer team in England, and as you can see, once again, data that you can get from the site, and the list, the names are on the left, and then they just put it in table nationality, position, goals. So there are no crosses, and so you can try to figure out a function, if any. So you see functions here. Let's start with this. So suppose the X inputs are the names of the players. Okay.
Number of goals.
Well, yes, but it's a function number of goals. What's the output? The output set, the codomain. Remember did I put that terminology for it? Yeah, so domain function codomain. So you have to specify the domain. I just did. Okay, then you have to specify before, probably better to specify the codomain before you specify the function itself. Okay, so what's if you want to speak of the goals, what's the codomain specifically? It must be a set. Set. What is the set?
Nationality, position.
No, let's finish with the goals. They certainly will have unrelated functions here, but if we take goals as our function, then what's the codomain? It's set of outputs. It's ambiguous. You can pick different ones, but what? Give me an example.
Like natural numbers.
Natural numbers. That's right. Pretty good choice, and you can see why you want 0 there. By the way, because it's possible to have 0 goals, especially if it's a goalkeeper. So natural numbers would be a good choice, even though you can anything bigger than natural numbers will be fine, because there would be no problem. But it is efficient, so we don't want to necessarily include negative numbers here. So probably is okay, natural numbers. Or you can pick the real numbers too, and once again, there is no problem, but this is most efficient. If you go with codomains for either position or nationality, then you're gonna have also, but you have to, in this case, these will be lists, right? So these are not numbers, so you have list of all countries as the codomain, or list of all positions as the codomain once again, and then you have a function. Okay, so unless somebody played 2 positions, in which case you have a problem, but then the table wouldn't work. Yeah, so yeah, that works out fine. So once again, this is the definition of a function as a procedure, a rule. It's one of those things. It's just as the set. We're not very careful about trying to define very specifically. This is, however, even though I'm using this loose language of a rule of procedure, but ultimately it's a bunch of pairs. A bunch of pairs with this extra condition. There is for each input there is exactly one output. That's really the condition. We visualize them with these blobs. Once again, emphasizing that there is no structure there, and then there are arrows from left to right. We also speak of independent variable. Dependent variables, you're used to that. I hope by now. But here in this context, the confusion that I encountered is about the word variable. What is the varies here? What varies here? Nothing varies here. All functions that we have had are literally a list. So it is written. It's done. There is no variability to anything, you would think. But you probably can make a case that you vary x. And you literally can go through x's, for example, and you see what's, well, not this one, but probably this example. You can go through x's and you can see how y's vary too. Okay, so you control, you have control over x, and if you want to change from a to b, you change it, and then you see what's happening to y. You do not change y at will. You can only change by changing x. So if you have a function, even though it is written in stone, you can still, because there are many x's, you can skip from one to the next, and therefore make a case for calling them variables. But the word comes from probably from calculus, why we want to call variable, especially so like if the independent variable is time, right? So then the dependent variable varies with time. Time varies. Once again, it is out of our control, but it varies, changes, or passes. And then for example, our location depends on time, and that's where the word comes from. But it doesn't have to. So it doesn't. There is nothing more behind it than there's certain particular situations when it has some physical meaning behind it. Okay. Okay, so this is how it can fail a relation which might not be a function. So two arrows originating from the same point, that's not a function. On the other hand, on the right, we have two points arriving to the same location. That's fine. That's not a problem. Similarly, we have no arrow on the left. That's why it cannot be a function. On the other hand, there's some of the dots on the right are missing, and there are no arrows arriving to them. That's okay. That's not. There is no restriction on x, only on y. I'm sorry. There is no restriction on y, only on x. That's that. Once again, two conditions imposed. Okay, so relation between x and y becomes a function from x to y, or it could be a function from y to x, depending on the circumstances. But the language could be the same, but seemingly, or rather, the language can be different. As you can see on the left, you use the either affirmative statement or passive tense. On the right, it's the same thing, same relation nonetheless. But when you speak of functions, the difference is crucial, and you cannot flip domain codomain without changing the function. Okay, so because once again the basketball is played by two boys, and which means that you cannot have you cannot have two outputs. So if you try to flip the arrows, you fail. Okay, so that's something to worry about. And okay, so when it's a function, and we will have to deal with that later. Okay, so let's take a look at the original problem of mixtures and see see where the functions are. There are no functions to begin with. There were actually they were relations. So there one relation was these are the two relations that we ended up with. These are. And then what you can do if you were to solve it algebraically, you solve for x or you solve it for y. Okay, both of them or one of them, and then it happens to be unambiguous, right? So very simple algebra applies, and so y is equal to 6 minus x, right? And then remember what you do with it. How to solve the problem. So once again, two relations, you need to find x and y. One way to do it is to solve for y, and then what?
Substitute.
And then substitute, substitute like this, maybe here. But the crucial step is, well, what we say, solve for x. That's we usually describe it, but now we can explain it in different terms. Express y as a function of x. Okay, it's the same thing, but it is indeed a function, so that we can substitute. So on the left are only x's, on the y is a single y, and so then the replacement of y makes sense. Okay. So set building, also probably familiar, but nonetheless, let's go over this. Some basic idea of what it means to solve an equation, and the answer is to produce all x's that satisfy the equation. What does it mean for equation to be satisfied? It means when we plug in a particular that particular value into our equation, we have a true statement. If it's false, if it's true, it's a solution. If it's false, it's not. And then we have to collect all of these x's that are acceptable and then put them together in a set. Okay, so the answer then to an equation is a set, not a number, not even two numbers necessarily, but you have to be very specific. As you can see here, we could be if we just try to kind of just experiment, then you might conclude that x is equal to 5, but how do you know that that's it? So you did some algebra, and then you know that x equals 5, and you know that's fine, x equals 5. 5 is a solution. Is there more? So that's a question we have to face very seriously in the environment that we're in. How many answers or how do we find all of them? Okay, so you can see in the third row here is that x equals 1. We know for sure that's not it. Okay, so these actual quadratic equations, they typically have 2. And so if you find 1, that's not, you're not done. Okay, so and the last one has nothing. So all of these possibilities will come up is 1, more than 1, less than 1. All of these 3 possibilities are there. And so when to solve an equation, you have to, you're sort of imagining, you can imagine that you are plugging in the values, and every time you test it for being true or false, just like this, 1 plus 1 is 2 is true, 1 plus 1 is 3 is false. And so every time you have a statement, a preposition, if you like, because after all, equal sign stands for is, so it's a sentence, and every sentence could, if it makes any sense whatsoever, could be true or false. It's the worst when you have a sentence that makes no sense and neither true nor false. So with equations, they're equations. So, but I guess you can have even equation which is that makes sense if you mix pounds with inches, for example. But generally speaking, it's an equation. It's either one or the other. So every action is tested this way, and that creates a set. Remember, what defines a set is a condition, and an equation could be a condition that defines a set. It's a test of whether it belongs or does not belong to the set. Okay, so equations. Have we solved these equations before? X over x is equal to 1. I did it just yesterday in my other class, and I'm not sure if I did it in this class or the other class. There's too many classes. So once again, even though you are usually do algebra to solve an equation, but sometimes you still imagine as if you are actually plugging x's into the equation, and that's especially if it's unclear, like especially B and C, it's unclear what the answer is. You imagine plugging an x into the equation, and then you will know whether you end up with true or false state. So x over x is equal to 1. Once again, don't try to solve it hypothetically, but imagine plugging in x's. What do you get? So, but for what x's is it true, and for what x's is it false?
Oh, okay. So any number, right?
Almost.
Any number except for 0.
Except for 0, yeah. Because you're still not allowed to divide by 0. So then the solution set, if I were to use a set notation, a set building notation, x not equal to 0, that would be the answer. Okay, so all right, and what is the solution for B? It's the same left-hand side. The left-hand side of the equation is the same. So what's as in C. So what?
So still the same as the left on A, right?
The left-hand side, yes, but the right-hand side is different. You cannot have simultaneously the same thing be equal to 1 and to 0, which means that whenever the C is satisfied, B cannot be satisfied. So none of the numbers have to be tested then, because all the numbers, x over x, you can cancel x and produce 1 as long as x is not equal to 0. So the only thing that needs to be tested is 0 in part B. And so which produces what? It produces the same problem as on the right, in C, 0 is 0, outside of calculus is meaningless. Okay, so which means that if it's meaningless, it's not equal to 0. Okay, because 0 is meaningful. So and the answer is empty. Okay. So the equation with numbers, even the numbers may pose the issues like this in front of you, and you have to deal with them. And the algebra may or may not save you, but also it also applies to these abstract functions that we have seen, and this is our running example of a function which every function will produce an equation in a particular way. Okay, so that's very convenient because then we can classify equations in terms of the function that are present. Okay, so that's some kind of abstract function, and then what is the meaning of an equation? Here in examples, you can ask questions. Which boys prefer basketball? Okay, so you can just look at the arrows and answer the question without trying to put a label on it, but it is an equation. Okay, so once again, which boys prefer basketball? It's a question of which axis will produce which axis will produce a particular y. So we pick a y, the output, and we're retracing our steps back. We try to find which axis have produced this y. That's an equation. That's literally an equation. So like this, where is it? Yeah. So find x y axis with f of x is equal to basketball. That's an equation. Okay, so you run through all of the x's in the input space, and to find all of them that will produce basketball as the outputs. And for each of the outputs, by the way, I can produce one equation. So the answer is for the and it will produce a different answer. In a way, as you can see, I put basketball, tennis, baseball, football in the right hand side, and then I'm supposed to find all axes. Which word does it produce is set sets every time. So we'll have what that's one set, the other set, third set, and one set is there's no for baseball there is no set. Well, there is a set. It just happens to be empty. Okay, so once again, one function, and for each of the possible for each of the outputs in the codomain, there is an equation in the literal sense as we can speak of, and then solving them would be our task frequently. Okay, so these equations, the solutions are here. So that's what the meaning of this idea. A solution of an equation with respect to x is an element. So we speak of a solution. Just watch the grammar. Is an element that, when put in the place of x in the equation, gives us a true statement. Okay. So once again, testing, plugging x's in the producing true or producing outputs, and as the output matches the equation, then it's a solution. If not, it does not. Ultimately, these are, as you can see, 4 equations produce these 4 solution sets. Okay, combine solution of the first equation, net one element in the set produces the solution set to the second equation. The empty set is the solution to the third equation. The fourth equation has the solution as the solution set can and C. Okay, so once again, these lists are complete. So there you cannot add or remove anything from these sets. Otherwise, the answer is incorrect. That's why the grammar is so important here. The solution set, okay, a solution that's one input element, and this solution set is the all of them taken together. Okay, so and that this is set building notation is could be a condition, could be an equation. Equations are very popular, producing sets of numbers, especially. And so which one is more important, solving equations or producing sets? It's the same thing pretty much. So once again, these we just did it. It's a matter of simplification. So this is a simplification. Once you start thinking in terms of sets, you realize that solving an equation is nothing but simplifying your solution set. You already have a solution set defined on the left, but it's defined implicitly with the formal equation. On the right, it's been so simplified that you don't have to do any more work anymore. Okay, so you end up with so it's literally a list if you can pull it off. you have that's what we need to solve the equation, is to produce the solution set in the simplest possible form. Okay, so okay, so okay, we already talked about that, or not? We didn't talk about that, but all right. Okay, we're not going to overdo the logic too much. So solution sets, so equations, okay, you can visualize them. We stick to numbers, we can easily visualize them with dots. So every number is a dot, and so we have 1, 2, 1, 1, 2, and nothing as the solution sets. Once again, we're rewriting our sets. X column equation, and then which is the solution set, and then the solution set simplified is on the right. Okay, so that's, in other words, it's algebra, if you like. It's algebra of sets. Okay, so and we just simplify. Okay, so all right, let's speed it up. XY plane, we already learned how to deal with the we learned how to build a line, okay, the a real number line. Okay, so that will come up again. But why do we need XY plane? To visualize functions. Once again, we saw it, it's called the Cartesian system. If we were to visualize a numerical function, so x is the domain, y is the codomain with arrows. That's the way I have done it several times, visualizing a function by arrows, indicating what the domain and codomain is, and then visualizing all the functions by means of arrows. Okay, so quite clear what this function does: transform x into y. You can even think about this like a piece of rubber, and what happens with there seems to be some stretching there. So that will comes up next. But how to visualize it alternatively, and we know that's the taking these two axes and putting them rather than parallel to each other, or we put them, making them perpendicular. So that's the only thing. Okay, so a different way to visualize a function is to the domains and codomains happens to be real number lines, but we put them, instead of aligning them as conveniently, it is convenient, and that emphasizes that we speak of a function. You can see where x goes, right? But we could try to plot we're creating, constructing the xy plane. We already know why we want to tables and graphs, and so let's forget about the function for a moment, and we take the x-axis and the y-axis and put them in such a way that any function would be there on the xy plane. So once again, x and y, so that's what we're building. So forget about function for a moment. And then we already know how to build x and y. I have x. That's what it looks like. It's a line with units, with the origin, with the arrow, and with the units. Okay, so in that order, I remember the line. Then you add the arrow. Then you add the unit. Then you mark the unit. Then you add the origin. Then the unit. Then you mark the unit in left and right direction. I'm adding another. I'm doing exactly the same thing with the y-axis, except the units might be different, and therefore the length might be different. So it doesn't have to be, but certainly it is. It is makes sense to emphasize that. So that's step one. Step two. So step one is the same as we're building two copies of the real number line. Okay. Then we arrange them vertical and horizontal. And once again, traditionally, they are arranged at they're joined at 0 to begin with, 0 aligned with 0, only 90 degrees. Neither one of these requirements is set in stone. So, for example, you may have seen it. Even Excel allows you to align to arrange the two axes not joined at 0. Okay, so it's possible. For example, if you were to speak of something historical, and then maybe this is 1901, and then this is 1902. Okay, and that's some kind of axis. Historical graphs, right? So you don't start at 0. There's no 0 AD, by the way. So that's a graph, and here you might be concentrating on some kind of production, and then it might start. This is 1000. This is 2000. Well, and then if you were interested in the change, then they might be like this. And then not only the horizontal axis does not start at 0, the vertical doesn't have to start at 0 either. So maybe this is 1000, this is 1100 or something like that. So it's also possible the two axes are not glued together at the origin to begin with. Okay, so that's that you just see a lot of that. It is just traditional, the simplest way to do it is in that manner. Also, the angle does not have to be 90 degrees for us to produce a coordinate system. That's what we speak of, after all. If they're sloped, it still works. You need to curl. You need to find where you are, and if your slope or your axes are sloped, it still works out as long as they are not parallel to each other. Anyway, so markings, vertical markings horizontal. So we create, we put, this is the frame, we put a fabric on it if you like. Okay, so we draw vertical lines for each of the labels on the x-axis, and the horizontal line for each of the labels on the vertical line. And there's a kind of, if it's a presumed to be kind of a fabric, a continuous fabric rather than what it looks like, a mesh. So fabric is actually, if you zoom in on with a microscope on the fabric, there you can see through. So that you can think of that exactly that. But our assumption is there are no gaps. We're not missing on any of the points. So it's literally just like the real number line is like either pencil or like a rope. There are no missing points. Here, it's a piece of paper. So there are no holes either. Okay, so that's what we want to construct, and that's why we need all the real numbers for the horizontal, all the real numbers for the vertical. It's called the Cartesian plane, XY plane. Notation is R2. Or it's not R2, but more like R squared, right? Because this is kind of a square, and then we'll have R3 and so on, and as many as necessary. In which case visualization becomes impossible. So ruler, if you have a ruler, how do I produce a plane? You have two rulers, and then some engineering paper, if anybody has seen this engineering paper actually exists, the one on the right, which is basically made of two rulers or measuring tapes, and then the vertical and the horizontal lines added together, and then you end up with this grid. Okay. I'm not sure they do it anymore, but you actually can see it right here. You can see, yeah. So there you can. This is rulers, grid lines, literally. Okay, so this is Paint, Microsoft Paint, and they have all of that, except the X's are not in the traditional way, but nonetheless it's still the same. As you're moving around, this is your x-axis. Your location as my mouse moving around, you can see in the bottom left, the coordinates are changing. Okay. So Excel itself also has same coordinate system, except in this case we only use integers, right? So instead of real and real, we have integers and integers. The idea is the same. Okay, so where am I? Okay, so resizing graphs. So once again, if you go to Excel, you plot it, and something to keep in mind, you can easily rescale it. Okay, so that's when you have two axes unrelated to each other, the entity, the quantities are maybe time and space. Why I can stretch it? What does it do to the idea of the data? The data remains the same. It's on the left. So keep that in mind. So you do not have to have squares in your graph as much as it commonly happens when you plot and you have it is square graph, but in reality of data, especially, it's simply not the case. There is no relation to x and y, and so squarely or not squarely, 1 inch and 1 pound, 1 inch and 1 pound. What do they have to do with each other? Do they have to be exactly 1 and 1? No, they do not. So it's ambiguity there is a little bit is unavoidable. Okay, so I just talked about that. So once again, coordinates is why we do it to begin with. In addition to functions, it's a coordinate system. Okay, we would have a coordinate system for dimension 1, so every location corresponds to a single number, and now every location corresponds to 2 numbers, and vice versa. Okay, so this is the basic idea of how you find your location on the grid. If you have a location, you draw a dot, an arbitrary point. You go vertically to find mark it spot on the x-axis. That's your x coordinate. You go horizontally, find the y coordinate, and you produce 2 numbers. So in this case, you have this random number. It produces a pair of numbers, 4, 1, and these are the 2 coordinates. Conversely, if you have two numbers provided, -2 and 4, what do? You find the 2 points, you remember the correspondence is the first one is x, the second is y. You find that x and draw a vertical line through it, that's the green one. Okay, so this is the green one, and then you find y on the y-axis, this is the 4, and you plot it, and you draw a horizontal line and they intersect. Okay, because that's why for the system to work, all you need here is that the two axes not being parallel, because if they're not, even there is an angle not 90 degrees between them, there will still, these two lines will intersect. It will give you one single position. Okay, so that correspondence between points and pairs of numbers will still work. With no problem whatsoever. The geometry will be all screwed up, but other than that, as a coordinate system, it works out just fine. X coordinate, Y coordinates. Okay, so once again, as I just mentioned, if you allow, okay, if it makes sense to you, z squared. What does it mean? If this was what?
Integer squared?
Yes, so this was r squared and this is z squared. So what does it mean?
Representative of Excel, how they use integers.
Well, because you cannot have a cell in between. Okay, so you have to use integers. The locations can have only integer coordinates. Okay, so either rows or columns. Okay, so then it's not really a Cartesian plane because of that. And so if you want to be fancy, that's how you get designated it. So it's a copy of C. You can actually see 1, 2, 3, 4, and another copy of C is a vertical one, and you combine them together with this square, which is really stands for multiplication, and then you have a model of Excel, even though just as well you can try to do n squared, and by the way, 0 is not included. Right, so you cannot have negative coordinates, unfortunately, in Excel, for better or for worse. Okay, so and they're in Excel, they are going in the wrong direction, just like with Paint 2. The first coordinate goes down, and the second coordinate goes horizontal. Yeah, so first coordinate row R go down, and the column C goes to the right, and so then it is RC. That's the system that you use. As you can see, Cartesian system is the opposite. X right, not the opposite, but differently. X is going to the right and Y's go up. Okay, so that's what you can actually plot the coordinates here for the x's on the left, integer x's, integer values, and then a bunch of points. Each of these cells has a numerical representation with two numbers, and you can use the Cartesian coordinate notation to label them. So that's what happened. What it is. It's also set. Okay, so let's everything we introduce a new player, and then it's probably is either a set or a function. So in this case, it's a set of pairs of numbers. R2 is pairs of numbers x and y, x real, y real. If you want z2, it's the same thing. Only this. What is z2? This is integer, and this is integer. Okay, so it's also possible. Any set can be created for that matter. Okay, so once again, we keep reviewing this. Operations on sets. You know operations on sets?
Section
Yes.
union.
That's right. So intersections and unions. Okay, so this is not these two sets don't overlap because no ball is a boy and boy is not a ball. So we do not there is no intersection to worry about. But the union, you can create a union. You can just pile up any two sets of any nature and create a new one. So literally merging. If you think about merging lists, that's what it is. So the order doesn't matter, remember, so it's not literal list, but you just bring them together, remove the border between them, and you create a new set. So that's entirely within our power. This is the notation that is literally a U for the union, and we creating set. And once again, you can rearrange the participants in any order, making it. This is the definition. The union of any two sets is the set that consists of the elements that belongs to either X or Y. So in the case of the overlap, make sure that you do not count things twice. So then over here, so all kinds of unions are computed here. So this is once again, if you want to connect sets with logic, that's what it is. For X to belong to X belongs to X union Y. Okay, then what does it mean? That's what it means. It means that X belongs to X or X belongs to Y. So one of the two is satisfactory. Okay, so either it is one of the boys or it's one of the girls, and that's how the union is to be. So merging lists without repetitions, like this, or merge literally, then remove repetitions. And then the overlap, technical term, is the intersection. So once again, the nature of the elements are unimportant. The symbol is upside down, and then you identify the terms that are, in this case, in another competing problem, right? So instead of merge, if we have done it before, this is what's the proper term? Match. I don't remember what the competing term here is. You have two lists, and you're supposed to go through them. Way more computation, by the way, and match one at a time. Each term on the left should be compared to one on the right. If they're repeated on both sides, you keep it. The rest are thrown out. Okay, so those three items: football, basketball, and one of the boys. And see who that is in the red T-shirt. They appear both on the left and on the right, therefore they are the only one that we were going to keep. Okay, so that produces the what we call the intersection. So okay. Notation is the set that consists of all the elements that belong to both X and Y. Once again, the logic is the word instead of or. Remember a minute ago it was or, and now we have and. So that's the match between the logic on the one hand, the language of logic, and the language of sets. On the other hand, they match up here. And then in logic, you have and or. In sets, you have intersection and union. So once again, it's not something to learn a lot, but rather accepting this as a language that clarifies things and be easy to communicate, especially when you use the notation, which abbreviates things grammatically, and then you'll just use it until you get used. Okay. So so two sets of solutions. So if you have one equation, then we know how we do it. We just discussed it. So you have an equation. Solution set is written in the literal sense, and then it's simplified and have the answer. What if you have two equations to be satisfied, just like whether it is one variable or two? So we have two variables when we spoke of the mixtures. But what if there's only one variable? So then what? Okay, and the answer is and. So literally, if you have a system of equations such as this one over here, then you want both of them to be satisfied. Okay, so you have one equation, you have the other equation, and if both of them are to be satisfied, then we speak of the intersection of the two sets, and then you can actually carry out the computation in the literal sense. You solve the first equation, you have answers 1 and 2. The second equation, they 1. Altogether, the only one that satisfies both equations will be the intersection, and that is 1. Okay, so the other two are thrown out. On the other hand, sometimes you want one of the two equations to be satisfied. I can think of one example. usually both, but it can happen, in which case you put or between the two equations. And then at the end, instead of doing intersection, you do the union. And once again, instead of ending up with one in the intersection, you end up with all three. So 1, 2, and -1, all possible, either satisfy one equation or the other. So it's also possible. Satisfies first equation and the second equation, or satisfies the first or the second equation. Inequalities. So we're not doing a lot of inequalities because they're sort of complicate things significantly, but they illustrate intersections very effectively. So one equation. So the first equation, x larger than 0, it is the blue one. The green one is x less than or equal to 3. So the two rays, one to the left, one to the right. And then we're supposed to find their intersection, which naturally is literally the overlap. So everything between 0 and 3 is the answer. Okay. So I once again watch the matching language here is and turns into the intersection, or turns into the union. So put the empty, so just read this stuff. This here repeat the definition, and yeah, we'll deal with that later. So this is what I just mentioned a second ago, is what if our sets are actually have on the plane to begin with. The sets are on the plane, and then we have two equations to be satisfied by these equations of two variables, which means that the solution sets are in fact on the plane. So the red one is the red one. Okay, well, that's better. So the red one gives you the first equation. So the first equation gives you the first solution set, and it gives me that's what the solution set looks like. Okay, now I go with green too. And then the second equation produces the second solution set, which is plotted here. Okay, and then the requirement literally is that both of the to have the blend of the coffee of those two types of coffee that is acceptable to us, both the conditions must be satisfied. And then we have and, which means that it is the intersection, and that's way back to making full circle that one single. Similarly, one single dot over there, 4, 2 is in fact the intersection of these two lines. Okay, so literally, if you want to summarize what has happened, that very simple algebra, but summarized now using the language that we have developed. So all x and y. So let's look at this. The first line, all x's and y's that satisfy first x plus y is equal to 6, and 2x plus 3y equals 14. Okay, so then we replace n with the intersection. Okay, we write these two separately. So the first set is xy with x plus y is equal to 6. Second one, x plus xy satisfying 2x plus 3 is equal to 14. Okay, so and then we have them plotted, and then once again green and red, and then looking for the intersection. It is the point that satisfies both of the conditions, and we have the answer. Okay, so once again, to appreciate the difficulty of the problem, why we illustrated in this something that might not need this complexity, but imagine that if you have even 3 ingredients in that cup of coffee, then we speak of the intersections of, remember, of what? So 3 types of coffee. We have then 3-dimensional space, and the restrictions say, how did it disappear? They're planes, as a matter of fact. They're planes, and so you have to think in terms of how possibly up to 3 planes intersect with each other. So visualization is pretty much out of the window, and so we have to be very careful in doing algebra properly. Okay, so empty, and these are the alternative. Remember, alternative setups when the prices may be different prices, and so then the intersection makes perfect sense. empty intersection, okay, when the price of two types of coffee is the same. So we, then the total weight and total price do not match and we end up with nothing, or they do, in which case we end up with everything. And so the solution set is a whole line, and then any point on that line will be acceptable as a type of coffee that that is required. Okay. Inequalities, okay, let's skip inequalities. Well, once again, inequalities are easy to visualize. I mean, two lines intersecting is pretty convincing, but here you can also see how every linear equation, inequality rather, determines a half plane. Just as every linear equation, x plus y is equal to 6, determines a straight line cuts the plane in half, and therefore there are two half planes. And two half planes intersect in this manner, as you can see, producing maybe a very small slice of acceptable possibilities. Okay, so I'll stop here. Class dismissed. If you have any questions.
Not gonna give us a.